The linear version of the Lagrange error term is basically a rearrangement of the mean value theorem, where we have the first approximation at f of c and our the remainder term being the first derivative term is going to be the error term for that linear approximation. So we can then extend this and find a quadratic error term. So in this case here, we have f of a equals f of c, that's our first approximation. And then we have f prime at c, and again, notice that's c and not b. So this term here represents the second approximation given our Taylor polynomial expansion. If we were to stop it at this point, the next term is going to be a Lagrange error term. And again, notice that the remaining terms can be calculated as long as we can find some point b. So this represents a quadratic error term. So it's extending that linear approximation to one more term. So what does this look like? So I've given you an example here of sine x, and we have our linear estimation is centered at 0, and we're going to evaluate it at pi over 2. So when we take a look at the sine x at pi over 2, it's equal to 1. That's that black dot. And the first picture I've drawn is when we have maximum error. So if I let b equal to 0, okay, so what I've drawn here is this equation where I have a slider for b, and if I let b equal to 0, you can see that the line that's going to get me from the center point to 0, the center point 0 here, to this point here, that's the point that I want. The blue line, when b is equal to 0, is way off. In fact, that is the maximum error that we could actually have by making b equal to 0, because it's at the edge of the bound of where b can be. Now, if we change that b value, so I've got a slider on here. So this slider, I can move left and right. So if I move that to 0.88, that's what I've done over here in the second picture. As I move it to 0.88, you can see that that actually is pretty close to the right b value, because that's going to then make that this term here is going to give me the right linear slope that's going to get me from the center 0 to the point A that I'm estimating at pi over 2. So that being the error term, I can calculate the exact error if I can find the exact point B. Now that's not necessarily feasible to actually find that point B. Here I've just estimated by using that slider. But when we do the error estimation, we're going to bound that point B, and we can bound it between 0 and, in this case, pi over 2. So here I've drawn this again. When we have a b value at 0.88, you can see that that is the b value that will get me from the center to the point that I'm estimating. And if I don't have a good b value, I can see that my estimation point is actually quite far off. That blue line is actually not estimating the correct point very well. And that gives us our max. The case that I've drawn on the left is actually the maximum error. So this is what I've drawn here represents the mean value of the mean value theorem in linear form. And this is just playing around with this. We can adjust the b value.